Ever get curious about what makes all our tech stuff actually work? Today we're gonna kind of peek under the hood at this super important concept and how computers, well, compute. It's called iteration. Basically, think of it like the heartbeat of a bunch of instructions. It's a loop, keeps going and going until the job's done. And the best part, you don't got to be a coder or anything to get this. It's a fundamental idea from computer science that anyone can grasp.
Absolutely. And to dive into this, we've got these really cool resources. They're excerpts from 3 video transcripts from this YouTube channel called Code Curious. Specifically, they're videos on, get this, AP CSP 381 iteration, AP CSP 382 iteration, and AP CSP 383 iteration. I know, real catchy titles, right? But seriously, they use this stuff in AP Computer Science Principles courses, so it's designed to explain these concepts in a way that makes sense, even if you're not a tech whiz.
Exactly. So what we're aiming for today is to understand how this whole repetition thing, this iteration actually works. Right. And also how it's described when we're giving instructions to a computer. Sometimes you see it in diagrams, they call them flowcharts, or in a simplified writing style called pseudocode. We'll get into all that. But the big thing to remember is that knowing when to stop repeating is super important. And getting this whole iteration thing isn't just for tech folks. It actually helps you understand how tons of processes work, even everyday stuff you encounter all the time. Ready to unpack all this?
Ready when you are.
Okay, cool. Let's start with something everyone can relate to, online shopping. You're looking for a new phone or whatever. You click on one, looks kind of cool. What's one of the first things you check?
Reviews. Gotta check those reviews.
For sure. I mean, who buys anything with a ton of bad reviews these days? No way. So thinking about this as an algorithm, there's this point where you're basically asking, are the reviews good? If the answer is no, the product's a dud, what do you do?
Back to the search. Gotta refine things, maybe try different keywords or just look for a different model,
Totally. It's like a choose your own adventure until you find the right thing, right? You keep coming back to those reviews.
Yeah.
But even if the reviews are stellar, we're not hitting buy just yet, are you?
Nope. There's another big question. Can I actually afford this thing?
Oh yeah, the budget check. So crucial. So if the answer to that is no, what happens?
Well, back to square one. Back to searching, maybe lower the price range, and then the whole cycle starts again. Reviews, price, reviews, price.
Yeah.
It keeps going until you find something that ticks both boxes.
Yeah.
Good reviews and fits the budget.
Right. It's such a perfect example because it's so natural, right? We do this without even thinking about it as an algorithm, but it totally is. Now, the video we're looking at brings up another relatable situation. Have you ever, lost something at home and had to search for it? Like your keys?
Oh yeah, all the time.
So the video lays out this simple algorithm for finding something you've misplaced. Let's say you're sure you left your keys somewhere in the house. How do you approach that?
Well, they suggest you mentally number the rooms. 1, 2, 3, like that. Then start with room 1, search it thoroughly, right? When you're done there, move on to room 2, search that one, and just keep repeating that. Search a room, move to the next until you've covered the whole house.
Makes sense, very systematic. But they point out something interesting, a potential flaw in this plan. What if you find your keys in the first room you look? According to the plan, you'd still keep searching all the other rooms, even though you already found what you were looking for. Have you ever done that? Kept looking even after you found the thing?
Oh yeah, I've definitely wasted time that way.
Me too. So this is where the idea of a stopping condition comes in, right? It's super important in any iterative process. Just blindly repeating stuff isn't always the most efficient way to solve a problem. In the keys example, a way better stopping condition would be, if you find the keys, Sato P searching.
Right, don't waste time going through the whole house if you don't need to.
Exactly, make it purposeful. Now the video throws out this fun brain teaser. It's a classic. The birthday problem. Imagine you walk into a room. There are 367 people there. Now, in a group that big, it's guaranteed that at least 2 people will have the same birthday. Statistically speaking, it's gotta happen. The question is, how do you actually find those 2 people using an algorithm? Why does this kind of problem need iteration in the first place?
But think about it. To find matching birthdays, you basically have to compare everyone's birthday to everyone else's. It's that constant comparing, that repetition, where iteration comes in.
Okay, so they suggest a way to do this. First, give everyone in the room a number, 1 to 367. Line them all up. Then, person number 1, they're the questioner. They start by asking person number 2, the starter, if they have the same birthday.
But it doesn't end there. Person number 1, they gotta ask everyone else in line, everyone with a number higher than theirs, about their birthday. Then person number 2 becomes the questioner and does the same thing, asking everyone with a higher number than them, and so on down the line.
Whoa, that's a lot of birthday questions.
It is, but with 367 people, you're guaranteed to find a match. But just like with the keys, we need a starting point. Once someone finds a matching birthday, they don't need to keep asking everyone else. They suggest if they have the same birthday, skip to step 9, meaning you can stop searching once you've got your pair.
Okay, so we've seen how this idea of repetition, this iteration, pops up in normal stuff we do and how we'd explain it, like, casually. But now, let's get a little more formal. The second video introduces pseudocode. What is pseudocode exactly?
Think of it like a simpler way to write out the steps of an algorithm. It's kind of like plain English, but with a little bit more structure. It helps you plan out the logic without getting bogged down in the specific rules of a programming language. It's like a blueprint for your code. And this video shows us 2 common ways iteration is expressed in pseudocode: repeat n times and repeat until.
Okay, repeat n times seems straightforward. You just do something a specific number of times. What about repeat until? Sounds like it depends on something happening.
Exactly. The video makes a key point about repeat until. The condition that tells you to stop repeating, that's checked before the instructions inside the loop even run. So if that condition is true from the start, the stuff inside the loop might not happen at all. That's a big difference.
Gotcha. That's a subtle but important distinction.
Yeah.
So let's see an example. Repeat 3 times. We have some starting values. X is 2, Y is 3, and Z starts at 0. Then inside the loop, we got to update these values. X becomes X plus 1, Y becomes Y plus 2, and Z becomes the new X plus the new Y. Walk me through those 3 repetitions.
Okay, first time through, X, which was 2, becomes 3, Y, which was 3, becomes 5, and Z becomes the current value of X, which is now 3, plus the current value of Y, which is now 5. So Z is 8. And that's just the first run. We got 2 more to go.
Got it. Second time through, X now 3 becomes 4, Y now 5 becomes 7, and Z becomes the current X, 4, plus the current Y, 7. So that's 11. 1 more to go.
Okay, last time, X now 4 bumps up to 5, Y now 7 goes up to 9, and Z becomes the current X, 5, plus the current Y, 9, which makes it 14. After those 3 repetitions, the pseudocode says to display the final values of X, Y, and Z. So that'll be 5, 9, and 14.
All right, so fixed repetitions, values changing each time. Got it.
Yeah.
Now let's see that repeat until in action. Here we have X starting at 2 and Y at 8. The instruction is repeat until X is greater than Y, and inside X becomes X plus 4 and Y becomes Y plus 2. So we keep repeating as long as X isn't bigger than Y.
Right, let's break it down. At the beginning, X is 2, Y is 8, so X is definitely not greater than Y. So we enter the loop. X becomes 2 plus 4, that's 6. And Y becomes 8 plus 2, which is 10. Still, 6 is not greater than 10, so we got to go through the loop again.
Okay, second time around. X becomes 6 plus 4, that's 10. And Y becomes 10 plus 2, that's 12. Still no good, 10 is not bigger than 12, so we keep repeating.
Third time's the charm. Well, X becomes 10 plus 4, making it 14, and Y becomes 12 plus 2, also 14. Now, here's a catch. 14 is not greater than 14, it's equal. So the condition X is greater than Y is still false. Got to do the loop one more time.
Ah, so we're really seeing how that condition is checked before each repetition. Okay, fourth time through, what happens?
Now, X becomes 14 plus 4, which is 18, and Y becomes 14 plus 2, so 16, finally. 18 is greater than 16, so X is greater than Y is true, and we break free from the loop. The pseudocode then says to display the final X value, which is 18.
I'm seeing how that loop keeps going until that specific condition is met. Now the video throws in another practice problem, and this one's sneaky. Gives us X2 and Y8 again, but this time the condition is repeat until X is greater than or equal to Y. Notice the subtle difference, greater than or equal to. It asks what X will be at the end. I think we can figure this out.
We can definitely try. So we start with X2 and Y8. We stop when S is greater than or equal to Y. Initially, 2 is not greater than or equal to 8, so we go into the loop. Inside, X becomes X plus 4, so that's 6. And Y becomes Y plus 2, making it 10. Is 6 greater than or equal to 10? Nope. So we loop again. X becomes 10, Y becomes 12. Still no dice. Loop again. X becomes 14, Y becomes 14. Now 14 is greater than or equal to 14. The condition is finally true. We exit the loop. What's X at this point?
It's 14, so that's what would be displayed, right?
You got it.
No.
It's easy to miss those little tweaks in the condition, but they can change how many times the loop runs. Big time. Those details matter. All right, one more practice problem from this video. We have this variable called product. It starts at 1. Then there's sum starting at 0, and another one, X, set to 3. There's a loop that goes 4 times. Inside the loop, product is updated by multiplying it by x, and sum is updated by adding x to it. Can we figure out the final product and sum after those 4 repetitions?
Let's give it a shot. First time through. Product becomes 1 times 3, that's 3. Sum becomes 0 plus 3, also 3. Easy enough. Second time, product becomes 3 times 3, that's 9. Sum becomes 3 plus 3, so that's 6. What about the third time?
Product becomes 9 times 3, which is 27, and sum becomes 6 plus 3, that's 9. One more to go.
All right, fourth and final time. Product becomes 27 times 3, which is, 81. And sum becomes 9 plus 3, making it 12. So after those 4 rounds, product is 81 and sum is 12.
Nailed it. But the video throws in a really interesting question here. What do those final values, the 81 and the 12, actually represent, given that x started at 3 and we repeated 4 times?
They want us to think about the bigger picture, not just the numbers themselves.
Exactly. What's the iteration actually doing? What pattern is it creating?
Well, if you look closely, you'll notice that 81, the final product, is just 3 multiplied by itself 4 times. In other words, it's 3 to the power of 4. And the final sum, 12, is a result of adding 3 to itself 4 times. Seeing these patterns helps us understand what iterative processes are really capable of. It's not just mindless repetition, it can lead to some pretty complex results.
That connection to exponents and repeated addition, that really clarifies the power of iteration. Okay, onwards to the third video. This one dives into the nitty-gritty of writing iteration in pseudocode and the potential pitfalls, the things that can trip you up. They stress that even tiny changes in how you write the iteration can have a huge impact on how your program behaves. And they introduce this kind of scary term, the infinite loop. Why is that bad?
An infinite loop is exactly what it sounds like, a loop that never ends because the condition to stop, it never becomes true. And that can be a huge problem. It can lock up your program, even crash your whole system because it's stuck in this endless cycle.
Oh no, that sounds like something we definitely want to avoid. So how do we ensure our loops actually stop? The video gives us this example. It starts with I initialized to 0, and there's this loop that says repeat until I equals 6, but the stuff inside the loop is missing. What do we need to put in there to make it run exactly 6 times and then stop?
The key here is that the loop keeps going until I is 6. So inside the loop, we got to make sure I actually gets to 6. They show us the missing piece. You simply add 1 to I in each repetition. It's written as I gets I plus 1.
Okay, let's trace it. I starts at 0. First time through the loop, it becomes 1. The condition I equals 6 is still false, so we loop again. I becomes 2, still not 6. This keeps happening. On the 6th loop, I becomes 6. Now, I equals 6 is true, and the loop stops. So I takes on the values from 0 to 6, but the instructions inside the loop happen 6 times.
You got it. Now, they show us how a tiny change can create that dreaded infinite loop. Same example, but they move where I is set to 0 inside the loop. What does that do?
Okay, so if we reset I to 0 at the start of every loop, then even if we add 1 to it later on, it just gets reset to 0 again next time around. So I never reaches 6 because it keeps getting pulled back to 0. That means I equals 6 will never be true, and the loop runs forever. Infinite loop city.
Exactly. It's a great example of how something so small, like where you put a single line of code, can totally change things. It can turn a normal loop into one that runs amok. It really shows how important careful, precise thinking is when you're designing algorithms with iteration.
Wow, a powerful lesson in how the placement of instructions really, really matters. The third video ends with this challenge. Write pseudocode to calculate the sum of the first 5 whole numbers, 1, 2, 3, 4, and 5. They give us a start. Sum begins at 0, a counter variable is set to 1, and there's n, which is 5. We have a repeat until loop, but the condition is missing. Inside, we add the current counter value to sum, and then increase counter by 1. What's the missing condition that'll make this work right?
All right, we need to figure out when to stop adding to our sum. We want the sum of the first 5 numbers, and n is 5. Inside, we're using counter, which goes up by 1 each time. We add the counter to the sum each time. So the loop should run as long as the counter is less than or equal to n, which is 5. Once the counter is bigger than 5, we're done. So the missing condition is counter greater than n.
Okay, let's see it in action. Sum is 0, counter is 1, n is 5. First iteration. Counter, which is 1, is not greater than n, which is 5. So we enter the loop. Sum becomes 0 plus 1, that's 1. Counter becomes 1 plus 1, that's 2. What happens next?
Second iteration. Counter is now 2, still not greater than n. Sum becomes 1 plus 2, so 3. Counter becomes 2 plus 1, that's 3. Still got a loop.
Third iteration. Counter is 3, still not greater than n. Sum becomes 3 plus 3, which is 6. Counter becomes 3 plus 1, so now it's 4. Keep going.
Fourth iteration. Counter is 4, still not greater than n. Sum becomes 6 plus 4, so 10. Counter becomes 4 plus 1, that's 5. We're getting close.
Fifth iteration. counter is 5, which is not greater than n, it's equal. So we enter the loop one last time. Sum becomes 10 plus 5, that's 15. Counter becomes 5 plus 1, making it 6. Now what?
Now, counter is 6, which is greater than n. The condition is true, so the loop stops. The sum at this point is 15, which is the sum of the first 5 numbers.
We did it. And the video reminds us with repeat until, the loop stops after the condition becomes true. So in that last step, the counter hit 6, and then we stopped. Wow, this has been a really cool exploration of iteration. Any final thoughts? What are the big takeaways?
The big thing is understanding that iteration, this idea of repeating steps in an algorithm. It's everywhere in computer science. We saw 2 main ways of doing it. Repeat n times for a fixed number of times, and repeat until where it depends on a condition becoming true.
And then that stopping condition, so important. We gotta avoid those infinite loops.
Exactly. And it's been cool seeing how iteration shows up in everyday life, like online shopping or finding lost stuff. Once you know about it, you start seeing it everywhere. Cooking from a recipe, using GPS, it's all about repetition until you reach a goal.
Mind-blowing how this seemingly technical idea is actually so common. Here's a thought to chew on. Think of something you do regularly, any task. How could you break it down into steps, an algorithm that uses this iteration idea? And what would be the stopping condition, the point where you know you're done? It's a fun way to apply these computer science concepts to your own life and see how things get done in the digital world and the real world. Thanks for joining us.